before we can illustrate the importance of these two numbers of 9 and 4 for this equation for the hyperbola that we've discovered, I'm going to have us look really quickly at a standard parabola. I'm trying to make it kind of big-ish, but this is just a standard parabola, y equals x squared. And so, yeah, you can see the points that are kind of plotted on there. And what you might notice is that if we try to take a straight line, which I'm going to use this ruler or yardstick to illustrate, any straight line that we place, say this one, actually let's get a little bit closer so that it almost touches right down here. So this straight line gets really close to the parabola right around here, but then as it continues, it gets further and further away from the yardstick. Again, if this yardstick were to continue. Now, if I were to change the angle just a little bit, now it's very, very close to this point right here, where x equals 3, y equals 9. It gets really close to the yardstick, but again, as the curve continues, it gets further and further away from the yardstick, right? This gap starts small and gets bigger and bigger and bigger, and if we were to continue both ad infinitum, it would get infinitely far away from the straight line. What I mean to kind of generalize that short demonstration is that if we put any straight line next to a parabola that is outside of a parabola, the parabola and the straight line will be divergent. And I'm not talking about the adult book series. What we mean by divergent is when two things are divergent, it means that they progressively get further and further apart. When things are convergent, it means they get closer and closer and closer until they meet. So for any straight line outside of a parabola, the parabola and that straight line will always be divergent. There may be a point where they come closest, but if continued to infinity, the curve of the parabola and the straight line will become divergent. They will get infinitely far apart. And we could, I dropped my yardstick and I'm too afraid to bend down and wake up Isla. But if we were to kind of play with the different angles, you would see that this is true no matter what angle you hold the stick at or the straight line at. You can get really close at some points, but ultimately it's going to become divergent in some, eventually. Again, assuming that it doesn't cross. You might be thinking, I'm going to try it anyway. There we go. Now you see it's getting pretty steep up there. So if you were to think, okay, well, what if I picked this angle of my straight line? Then it seems to be getting closer and closer to the stick. Now that looks true, but if we were to continue these two ad infinitum, this straight line would actually intersect our parabola. That parabola is going to continue and would either intersect the straight line or it would get really close and then get infinitely far away. This is all to say that what I kind of said before, any straight line outside the parabola is either going to intersect that line or get infinitely far away from it, which is why the hyperbola is super cool, because the hyperbola does not behave in that way. The hyperbola has what are called asymptotes. An asymptote is something that is approached and gets infinitely close to, but will never meet. So unlike the straight line of the parabola, there is a straight line, technically two straight lines that the curves of the hyperbola are going to get infinitely close to, namely it's going to be convergent, but it will never meet. A former teacher of mine once compared the asymptotes in the hyperbola to a French movie, where the two lovers get so close to meeting, but they never actually meet. Excuse me. So where are these lines then? I've already kind of sketched this green rectangle, and I got that rectangle from these two numbers, the 9 and the 4. Lengthwise, it is 3 in both directions, right? So this goes out to plus or minus 3. And up and down, it goes up to plus or minus 2. The square root of 4 is plus or minus 2. And if we were to draw the diagonals of this rectangle that I just sketched and continue them ad infinitum, these would be the asymptotes. So let's see if we can do that with a moderate amount of success. All right, let's see about this. So this diagonal here is going to pass through the origin, through the other corner. Let's continue in the other direction. Ah, that is a bad angle. It's not as dramatic over there, but that's because my curve is probably jacked up. All right, so let's see about sketching this one. All right, cool. All right, now obviously it looks like they meet right here, but in reality they wouldn't. That's just because I'm not very good at drawing straight lines, and I'm dealing with wide-tipped markers. So the two lines that I just sketched are asymptotes. The purple curve, the hyperbola, is going to get infinitely closer and closer and closer to the red line, but will never meet it. If you were to continue these forever, they will never meet. Likewise in this direction, in this direction, in this direction. All right. This explains how these two numbers play a role in the shape of our hyperbola. The hyperbola is not unbounded like the parabola. It is tending toward something. The hyperbola isn't just a crazy curve. It is getting ever closer to a boundary, and that boundary consists of these two asymptotes. And we can derive or we can understand what these asymptotes are pretty easily. They're straight lines, so the equation for that is going to be pretty easy, right? We all remember y equals mx plus b. And again, for our purposes, the center of our conic sections are all going to be the origin, so the y-intercept for both of these asymptotes are going to be 0, so we can just ignore b. So it stands, the only thing we need to find out is our m, our slope. That is where the square root of 9 and the square root of 4 come into play. So let's take this red line that has a positive slope first. We're going to rise 2 and run 3. So that has a slope of 2 over 3. All right. And this other asymptote is going to do the same thing, except it's going to be negative. We're going to drop 2 and run 3. So our two asymptotes are just plus or minus 2/3 x. All right, well that's easy enough. Okay, so to recap, we have discovered an equation that will get us a hyperbola. And these hyperbola, these two curves, are infinite in opposite directions, open, and are not going anywhere and everywhere they want. They are bound by these two asymptotes. They will get infinitely closer, but will never meet. I think that's lovely. Just that idea is crazy, that no matter how infinitely far you extend these two lines, they will never meet. So let's take a look at a short proof to demonstrate that this purple line and this red line will never meet. To prove that the hyperbola and the asymptote will not meet ever for infinity, we're going to use the same kind of method that we used in a previous video called the reductio ad absurdum. You remember this method? I call it the Sherlock Holmes method, where we're going to assume that what is false is true. And you know what assuming does. And then if by assuming a falsehood to be true, we get an absurdity, that proves that our initial assumption must have been wrong. So let's assume that the hyperbola and the asymptotes do meet eventually. I have them written up here, just the equation for the hyperbola, and then asymptote 1, asymptote 2. I'm going to use asymptote 1 for now because it's positive, and I'd rather use positive numbers rather than negative numbers. All right, so think about what that means. If the hyperbola and the asymptote at some point at infinity were to meet, that would mean there would be some coordinate, some x and y, that they have in common. Right? That makes sense. That's essentially what we were doing with the systems of equations. We would say if these two lines intersect, there's going to be some point that they have in common, some x and y that you can plug into both equations and get a non-absurdity. So that's what we're going to do. We're going to assume that there is some common x and y between the hyperbola and asymptote 1. Let's assume that we know where that is. If we know where that is, then we can substitute any x in the or y in the hyperbola for any x and y in the asymptote, or vice versa. So for step 1, we're just going to have our x squared over 9 minus. Now instead of writing y squared, I'm going to use this and use substitution to put in 2/3 x for y, right? Because if there is some common x and y, then I should be able to substitute and not have any problems. So rather than writing y, I'm going to write 2/3 x quantity squared, that's all over 4, is equal to 1. Okay, so I've done my substitution, so now it's just going to be a lot of algebraic footwork. Step 2, we're going to have x squared over 9, that doesn't change. 2/3 squared is going to be 4/9. X squared is going to be x squared, and then that's all over 4. Okay, easy enough. And then third step. All right, let's try to get simplified this business because we have a fraction in the numerator. So all of this is divided by 4. That's the same thing as everything times 1/4. Just over here onto the side. 4/9 x squared times 1/4. Those 4s are going to cancel out. We're going to end up with just x squared over 9. All right, so we get x squared over 9 minus x squared over, that's still equal to 1. All right, well, x squared over 9 minus x squared over 9, that is all equal to 0. This is our fourth step. We get 0 equals 1. But that is absurd. Which means that our original assumption must have been false, that this substitution was not legitimate. Therefore, the asymptote and the hyperbola will never meet. They have no common x or y. Otherwise, we would not have gotten this absurdity down here. Anyway, so I just wanted to show that quick proof to demonstrate that the asymptote and the hyperbola will, in fact, never meet. They have no common points. Even if you were to extend them to infinity, they will never, never touch. Just get ever closer and closer to each other, but never actually get there.